Hi everyone, this is Chen. I'm very glad here to present our paper entitled PGC, Decentralized Confidential Payment System with Auditability. This is a joint work with Xuecheng Ma, Tang, and Ellen. Here is an outline of this talk. We start with the background. In payment system, privacy can break into confidentiality and anonymity. Fix a transaction. Confidentiality means that no adversary can figure out the transfer amount, while anonymity means that no adversary can figure out the identities of sender and receiver. Besides privacy, another important property in payment system is auditability, which roughly means that an auditor can specify a set of transactions and then ask the relevant participant to prove their compliance with some specified policies. In centralized payment system, the transactions are kept on a private ledger, only known to the center. The center is in charge of validity check as well as protecting privacy and conducting audit. In decentralized payment system, for example, the blockchain-based cryptocurrencies, all transactions are kept on a global distributed public ledger. For example, the blockchain. To ensure public verifiability, Bitcoin and Ethereum simply expose all transactions information in public at the cost of sacrificing privacy. Privacy and auditability are crucial in any financial system. We want to know, in the decentralized setting, can we have the good of both? In our point of view, strong privacy is a double-edged sword. While confidentiality and auditability may coexist, anonymity seemingly denies the feasibility of efficient auditing because it provides plausible deniability. In this work, we treat anonymity for auditability, proposing the first auditable decentralized confidential payment system in the account-based model. Here is a simplified framework of auditable DCP system. Each user is equipped with an account. Alice can make a confidential transaction to Bob. The miner will check if the proposed transaction is valid. If it is, the transaction will be recorded on the ledger. Otherwise, it will be discarded. An auditor can specify a set of transactions and request the participants to prove their compliance with the policies. Next, we outline the desired functionalities and security of auditable DCP system. The first one is verifiability, which means that validity of transactions must be publicly verifiable. The second one is authenticity, which means that only the sender can generate transactions. Nobody else can forge. The third one is confidentiality, which means that except the sender and the receiver, nobody learns the transfer amount. The fourth is soundness, namely, even the sender cannot generate an illegal transaction that passes validity check. The last one is auditability, which requires that participants cannot cheat, and the audit is privacy preserving. The next question is how to achieve this functionality and security by choosing appropriate building blocks. We choose actively homomorphic public key encryption to ensure confidentiality, and choose signature to ensure authenticity, and choose NIZK to ensure verifiability, soundness, and auditability. Next, we show a subtle point. Note that we employ a public key encryption scheme and a signature schemes simultaneously to secure auditable DCP. Generally, there are two strategies that we can follow, namely the key separation and key reuse. The key separation strategy means that each account is encrypted with two key pairs, one for encryption, the other one for signature. The advantage of key separation strategy is that PKE and signature schemes are off the shelf, and the security of the resulting DCP system is easy to analyze. The downside is that the key size is doubled, and the address derivation turns out to be very tricky. The key reuse strategy means that one key pair is used for both public key encryption and signature. The advantage is that it will greatly simplify the design of the DCP system and make it more efficient. The downside is that it requires case-tailored design. In this work, we choose integrate signature and encryption scheme, namely the ISE schemes, in which one key pair is used for both encryption and the signing, while the INT CPL security and the EUF CMA security must hold in the joint sense. Our generic construction of auditable DCP system is based on two building blocks. The first building block is ISE, whose encryption component is actively homomorphic over Z modulo P. Fix the public parameters. The keychain algorithm naturally induces an NP relation R key defined as below. The second building block is NIZK, which should have adaptive soundness and adaptive zero knowledge. Next, we show how to build auditable DCP from ISE and NIZK in a general manner. To build up the system, a setup algorithm generates public parameters by running the setup algorithm of ISE and NIZK respectively. The public parameters will be used as an implicit input for all algorithms. To create an account, each user runs the ISE keychain algorithm to generate a key pair, in which the public key will serve as the account address, and then encrypts the initial balance. To reveal balance, a user just decrypts the encrypted balance, uses his secret key. Suppose the sender wants to transfer V coins to a receiver. The sender generates the confidential transaction as follows. In the first step, the sender encrypts the transfer amount V on the public keys, PKS and PKR respectively. The memo includes two public keys and the resulting ciphertext. In the second step, the sender generates an IZK proof pi-cracked for the memo information belong to the language aircraft. The language aircraft can be further decomposed as conjunctions of three sub-languages, in which the language L equals stipulates that two ciphertext encrypts the same value. The language L right stipulates the transfer amount lies in the right range, and the L solvent language stipulates the sender account is solvent. The sender then signs the concatenation of serial number, memo information, and pi-cracked into a signature sigma. The entire confidential transaction consists of the serial number, the memo info, the correctness proof, as well as the signature. Here is the data structure of the entire confidential transaction. To check if a confidential transaction is valid, the miners first check if the serial number is a fresh one of PKS, then checks the validity of signature and zero-knowledge proof. As soon as a confidential transaction is recorded on the ledger, the sender updates his balance by deducting CS and increments the serial number. The receiver updates his balance by adding CR. Upon receiving an audit request, participants use secret key as witness to generate an zero-knowledge proof for a collection of transactions satisfying the specified policy F. We list some useful policies as below. The first one is limited policy, namely the sum of transfer amount is less than a given bond, which is useful in anti-money laundering scenarios. The second one is rate policy, namely V1 over V2 equals to some prefixed rate, which is useful in tax payment scenario. The third one is open policy, namely the transfer amount is indeed some value V star, which is useful in selective disclosure scenarios. The auditor can then check if the policy is satisfied by verifying the proof. While the auditable DCP framework is intuitive, secure and efficient instantiation requires clever choice and the design of the underlying building blocks. The first goal is that the transaction generation and verification should be efficient and the transaction size should be compact. The second goal is that the system does not require a trusted setup. The third goal is that a system is hopefully can be built from reusable gadgets. We begin with the design of ISE. The most natural choice of the encryption component is exponential L-gamma PKE. Looking ahead, we will use the state-of-the-art bulletproof to fulfill the range proofs because it does not require trusted setup and is based on the discrete logarithm assumption. A problem here is that we cannot directly invoke bulletproof on L-gamma ciphertext since the secret key constitutes an oblivious trapdoor. In the literature, there are two methods to solve this problem. One is the quiz-quiz approach, namely generating a Pearson commitment as well as a consistency proof. A downside of this approach is that it brings extra bridging cost. Another approach is due to Zither, which requires dissecting bulletproof rather than using bulletproof in a black box manner. In this work, we overcome this problem by twisting the standard L-gamma, yielding twisted L-gamma, in which the second component is exactly a Pearson commitment without a trapdoor. Exactly for this feature, it is bulletproof friendly. We can thus directly invoke bulletproof on the twisted L-gamma ciphertext. Here is a comparison to the standard L-gamma. We can see that twisted L-gamma is almost as secure and efficient as standard L-gamma, while it has no bridging cost with bulletproofs. As an independent interest, we also implement twisted gamma as a standalone public key encryption. Compared to the widely used Palia public key encryption, the performance of twisted gamma is much better than that of Palia PKE for small message space. As to the signature component, we choose the Schnorr signature, whose setup and keygen algorithm are identical to those of twisted gamma. We prove that the resulting ISE is jointly secure because the signing algorithm of Schnorr signature is irrelevant to the decrypt algorithm of the twisted gamma. Due to the nice algebra structure of twisted gamma, we can prove all linear relations over exponents via sigma protocols and prove range statements use Boolean proofs. In this way, all accompanying zero-knowledge proofs can be realized efficiently and does not require trusted setup. Due to time limit, we skip the details of the zero-knowledge proofs and optimizing tricks. We implement PGC as a standalone cryptocurrency. The experimental result demonstrates that PGC enjoys good computation and bandwidth efficiency. Finally, we compare PGC with two related works, namely ZK Ledger and Zither. All the three systems are based on the discrete logarithm assumption and support transparent setup. For ZK Ledger, its efficiency degrades linearly in the number of system users, and the auditing efficiency depends on the number of history transactions. For Zither, whether it supports auditing is unclear. As to PGC, it achieves efficient fine-grained auditing at the cost of sacrificing anonymity. We conclude our work as below. We propose a framework of auditable DCP from ISE and NIZK with a formal security model and rigorous proof. We then instantiate the auditable DCP framework by carefully designing and combining cryptographic building blocks. The resulting PGC does not require trusted setup. The overall design is modular, simple, and efficient. Moreover, it supports efficient fine-grained audit. As independent interests, we propose a novel public key encryption scheme called Twisted Gamma, which is efficient, homomorphic, and zero-knowledge proof friendly. Therefore, it could be a good alternative to the existing ISO standard homomorphic encryption schemes, namely the exponential gamma public key encryption and the Palia PKE scheme. Besides, we designed two accompanying proof gadgets, which are widely applicable in privacy-preserving scenarios. For example, the secure machine learning scenarios. That's all. Thank you. Thanks for your attention.